Okay, so in this video clip, we're going to estimate a Cox-Ross-Rubinstein tree in Python, and the code we're using is going to be optimized for dynamic memory. The original code I obtained here was from this GitHub from Tian Yuz. If we can just spot the name here. Yeah, this Tian Nuz, and he provided, or she provided, Lysenheimer code and then Lysenheimer implied volatility code. If we take a quick look here, you can see that basically the structure of the code is based on the Espen Haug textbook, The Complete Guide to Option Pricing Formulas by Espen Gardner Haug 2007. So it basically follows very closely the VBA code. But the nice thing here is it outputs, okay, we can output Greeks, but the nice thing is we just need to change the U and the D estimation here to convert this Lysenheimer tree to a Cox-Ross-Rubinstein tree. So if we go back to the portal, Vinegar Hill, I took Tian Yu's code and just basically changed U to be e to the power of sigma square root of t, and then d equal to 1 over u. And then we calculated the risk neutral probability p as e to the power of c. Here is the cost of carry. It's the same as b in the original Espen Haug code. So cost of carry times the time step minus d over u minus d. Now just making that small change there means that this whole segment of code can be converted to a Cox-Ross-Rubinstein binomial estimation as opposed to the Lysenheimer. Okay, so to implement this code, very simply, we're going to copy the segment of code and go into an online compiler, which is probably the easiest to run, right? So, and we'll compare this to a Cox-Ross-Rubinstein tree set up by Espen Haug in Excel. Okay, so I'm going to go into an online compiler, online GBD, and I find this quite a good tool, and it's fast in the sense of setting up. So we just note that we must select the language here. We can paste in, and we'll get a number of outputs, not just the value of the option, but also we get delta, gamma, and I think theta. Let's just run this. And this is for a put option. So we have the value of the European call is 1043. Okay, let's look at our parameter inputs. S is equal to 100. So that's the stock price. The exercise is 100. T is equal to 1 year. R is equal to 5%. C is equal to 5. That means C is R negative Q. That implies that Q, the dividend yield, would be 0. The volatility is equal to 20%, and we've 100 steps. Okay, so we have these values here, and the price of the European call is 1043. The American call is 1043. The European put option is 550, and the price of the American put option is equal to 6. So that's fine. Now we can do something here that if we change from P to A, then we get the entire output for the price of the option. So what we have here is the prices of the options. European, American call, American call, European put, American put. If we change in the arguments here from P to lowercase a, okay, we get a number of Greeks as well. So A, and we must change this to A, and A. So no longer are we getting a value for just the price, but we're going to get some Greek output as well. We're going to get a vector value. So let's run that again. And it takes a second or two. So the value of the option is this 1043. The delta is 0.63, and the gamma is 0.0189. And likewise for the American pot. Okay, so we can copy these values. Let's copy this output. We'll go into a spreadsheet, Espen Haug's spreadsheet. So share screen and get into the spreadsheet. And I'll just paste our output here. So we better be a bit careful. Paste special, and we'll just say Unicode text. Right, and we could make it, perhaps I'll do that again. We'll paste here so we get a full view. Paste special Unicode text. Okay, so this is the value of the option. This is the gamma. This is delta. Okay, now the parameters, inputs, the arguments, the stock price was 100. Again, this spreadsheet is based on Espen Haug's textbook and VBA code that he left in here. Remember, this was 1 year. This was 5%. 5C is B. So cost to carry 5, 20% volatility, and 100 steps. And if we look here, you can see 1043. The delta is 0.6365, and we have the gamma 0.0189. So that's consistent. Let's change this to American. Will make no difference this time because different is 0. And we get the same values as before. What if we change it to a European put and run again? European put and run again. European put, let's go put. We get 555. Okay, European put 555. The value of delta is -36, -36. The gamma is 1.89, and we have no value here for theta. And then if we make this American, in this instance, it will be optimal to exercise early because we have it's a European put, despite the fact that the dividend is 0. Okay, so the values, are they consistent? You can see that the American put is more valuable than the European put, and that's consistent with economic theory. The gamma, correct, and the value of delta is consistent in both cases. Okay, so this code that we have introduced here, let's go back to our code. This code here produces output consistent with the original Espen Haug code, Espen Haug. And a big advantage of Espen's Haug is that the vectors, the memory storage is constructed so it's dynamic. And we don't store a static tree. We pass values from one time step to the next. And that's a very efficient way of using memory, and tends to be, as a result, a little bit faster. So all else being equal, this dynamic tree would typically be faster to run than a static tree. Okay.